Welcome everybody in Cyberland. Some of us have been here for a while. Those of us who are here, those lucky few, are doing a quiz. We're doing a quiz. Those of you in Cyberland who don't want to be left out of this quiz can find it in the sample entertainment. So way back in the beginning of the course, on the course webpage, right at the top is sample entertainment. And appearing there are 4 problems that we've actually, with the first 3 we've already discussed in the course, and the 4th one is what we're going to discuss now. And we're starting by you're working on these problems. You're going to try these to solve this problem. So this is the last one. These 4 problems might represent, if you understand these 4 problems, you've learned what we have to teach in this course. This is pretty much the summary of the whole thing, these 4 problems. So there's this 4th one. This 4th one's kind of nice. Yeah, I like how people come in. You see, we're doing a quiz, and you're looking, you come in, what's wrong? It's like you didn't miss anything really major. It's ungraded, there's a quiz, it's problem 4. Don't get shocked, don't suffer any problems here. For people, so people who are in Cyberland should be going back to the sample entertainment page on the web page, right up at the top. It's the link right at the top. And there's a list of 4 problems. And what we're going to discuss at the beginning today is problem 4, which is called driving back and forth. And so the idea is to start. We're going to start by spending 5 or 10 minutes seeing if we can solve that. I suppose it's roughly correct that if it's easy to solve, you should be excused from the rest of the class, and you should go you should go to one of the cafeterias and sit down and have, enjoy yourself. If this is totally obvious, you should maybe you don't need to be here. Some people have recognized that they don't need to be here anyway. But okay, go ahead. Go ahead. Yeah, you remember that there was a major exam, the 3rd midterm today? We're doing that 4th problem here as an ungraded quiz. So just the 4th problem. Well, if you finish the 4th problem, you can go back and review and see if you can do the first 3 as well, just to make sure you're remembering what we were doing here before. Oh, yeah. Problem 4. Problem 4. Ungraded quiz. You have to work fast. Ah, Sasha, welcome. Welcome. We're doing this, fortunately, ungraded quiz. Problem 4. Okay, I should start babbling. I can't contain myself anymore. Probably you've thought long enough. The issue is not so much the final calculation, but as how to think about this problem. Okay, so we probably, hopefully you were engaged enough to think about it, and maybe it's clear. So I have the points that I want to make about this problem here. Here, I don't know if you can see this well enough. This is my commentary. Dirt reverses conventional wisdom, and there's a certain calculus thing here. So what is the calculus thing? Does anybody want to what is the calculus here that you want to know? A little bit of calculus. So this is inviting a calculus thing. So what if I wrote, does this resonate? That resonates, you're really in business. That may be so easy calculus that you don't consider that that's worth mentioning, but that's the calculus you need to know. This thing here, this little thing here, this is the calculus. So this is a nice, I like this problem. It's really nice. It combines the course with the stuff that you, it combines high school physics type questions, elementary high school physics questions or SAT questions with probability at the same time. So, right? So that's this stuff here. Okay. One part about this is nice is most of the time, I mean, there's actually you gotta figure out what your professor's going to be like. So actually, this is actually the one approach. I mean, my approach I try to do is actually, as you discover, is I try to make the answers come out nice. They come out simple. So you do, like if you're doing a normal approximation, maybe the variance will actually have a square root you can compute. That would be nice. So when you're doing it and you see, oh, the variance is a perfect square, like 225, so when you take the square root, it'll be easy. You don't have to do any arithmetic. Okay, so this reverses at least the conventional wisdom would be look for the easy answer. Look for the trick that would give you the easy answer. So here, there is an easy answer, and that ain't it. Okay? So this is maybe more common. I mean, this is also another strategy, is you put in front of you the easy answer right up front. So you see the easy answer. Oh, yeah, just write this down, the easy answer, and you're done. And the point here is this, the easy answer. What is the easy answer? The easy answer here is a half. Right? Easier answer is half. You're sort of, on average, you're going 50 miles an hour on average in each direction. On average, you're going 50 miles an hour in each direction. So, sort of, on average, the same speed in each direction. So, you ought to spend about half the time going each direction. Okay, that's the look for the easy answer says slap down a half right away. Okay, that's a sort of at least somewhere in this process, you should at least be getting there, slap down a half, and either get that you did that or you rejected it for some good reason. Now, we haven't even inserted this part. This and this we haven't got to yet, but the sort of easy answer here is, oh, it looks like it's a half. Boom, we're done, right? And then one point of this is that actually is not the right answer. And that has to do with this here, this calculus here. Okay. Now, this has to do with the SAT stuff, the high school physics stuff. I don't know if does this resonate with anybody? I may be in a different time warp, space warp from all of you, right? That's always possible. What is this? What is this dirt? What is dirt? Robbie? Okay. Do they do that in Florida and Montana too? Right? I don't know. Okay, right? But not nowhere else in the world. Okay, distance equals rate times time. Okay. Okay. Well, once you hear that, you don't forget, right? This is the right physics course. If you took whatever physics course someplace, you should be full of things like that you will then remember it forever. That distance equals rate times time. Okay, so then that's the part that has nothing to do with this course, but that's probably the hard part. As usual, the stuff that has to do with the course is easier than the other stuff, probably. So this distance equals rate times time is, well, one might actually spell it therefore this way, right? Or this way. But anyway, that's the dirt we're thinking about. Okay, that's the key thing that's going on here. So you're actually asked about time. You're asked about time. You're asked, what proportion of the time do you spend going from Atlanta to Boston and suppose to Boston to Atlanta? What proportion of the time? The question's about the time. But you're actually told information about the rate. You're told the speed is random. The speed is random. One way it's this, the other way it's that. The speed is each way is a random variable. So you're given information about the rate, but you want to know about the time. So that means you need to use dirt to get the thing set up right. That's before we even get to this course, right? We haven't done anything in the course. This is like if we didn't have it random and you were told that you go at you drive, this is the SAT question, right? The truck driver's driving 40 miles an hour going from Atlanta to Boston, and he drives 60 miles an hour going the other way. What fraction of time does he spend there? No randomness, right? The dirt will do it then, right? The dirt will do the thing there because you need it, even if it's fixed, right? It doesn't have to do with randomness. We're discussing problem 4. You're in time for the dirt, to get the dirt on problem 4. Okay, so, well, and then therefore, this 1 over x comes in because we've got time is equal to distance over rate, and we've got information about the rate. So that's why we're doing this 1 over x here in the calculation. Okay, well, let's think about this from the perspective of this course. From the perspective of this course, you draw some picture about how you're in Atlanta, Boston, so you have time. Time is advancing. Time t is advancing this way. And you say you start maybe in Atlanta, and you go to Boston, and then you're in Atlanta, and then Boston, Atlanta, Boston, so forth. So then there's a time, let's call this could be x1. This is the time to go from A to B. And there's a time to go from B to A. And this is maybe x1, y1, x2, y2, x3, y3, and so on. So these times in this picture are, the x's are independent and identically distributed, and the y's are independent and identically distributed. So we have these random times. It takes a random time to go from Atlanta to Boston, x1. It's distributed as this. It takes a random time to go the other way, distributed as this. It takes, so on. So the x's are IID, the y's are IID, and they're independent of each other. This is an alternating renewal process because you have 2 of these variables. If you look at these times, Atlanta, every time you're in Atlanta, it starts over, right? Or every time you're in Boston, it starts over, right? It starts over either at the A's or at the B's. And since so that if you look at the A's, it's a renewal process where the times between renewals are distributed as x plus y, right? So that's the renewal process that I guess you could focus on from A to A to A. But when you have XY, 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 it's a special case of an alternating renewal process because it's really got extra structure. But all you really need to know is every time you're in Atlanta, you start over, and that's a renewal process. So we could do, just like we did last time, we could talk about the long run. We can apply the renewal reward process and talk about the limiting here. So in the renewal reward process, we would have the expected length of, we would have the expected reward per cycle, and we would have the expected length of a cycle. And that's the long run proportion. This is the long run reward, the long run reward. But now in our case, we want to structure, we want to define that. So we want to say we get a reward of 1 per time at rate 1 whenever we're going from Atlanta to Boston. And we get a reward of 0 here. And then, so the cycle is, so you think, well, what's the expected length of a cycle? A cycle is x plus y, so this is just That's the expected length of this cycle from Atlanta to Atlanta. And then you want to know what's the expected time that you spend going from Atlanta to Boston during that cycle. And this is just this. And in an alternating renewal process, when you want to know what's the long-run average time you spend in each of these states, it's going to be the same formula. The expected length of the one divided by the sum of the two. Right? And this part is all the stochastic process. It's kind of elementary. Just use this renewal reward theorem that says, that it's going to say the sum of the rewards to n of t over t is going to go to the expected reward, and this is the cycles, not ours. This is a different x, but this is really for us x plus y, I guess, if I put this here. But anyway, this is the expected cycle length, which in the general model is x, but here is x plus y. Okay? So this is our standard course approach to this problem. Boom. So I guess if you were doing this on an exam, you actually should separate out the stochastic process stuff from the SAT stuff. So you'd say, well, this is an application of the renewal reward. The long-run proportion is this. It's this. Okay, right? It's this. You'd write all this down, and you're sort of getting like you know what the theorem in the course is saying it should be. That would be good. This is just a strategy to say it would not be good to just write. You might know all this, and to write this down with no comment would be bad for all sorts of reasons. Even if you did know, you wouldn't get credit for it. Okay, you don't want to just write this, even though it's, in addition, it's the wrong answer. But you'd want to write this down here, and you're all right here. So that's this. The 4106 is what we discussed before. The renewal reward theorem saying these long-run averages are just expected reward. They're all in terms of expected value, expected reward per cycle divided by the expected length of the cycle. And almost everything in the chapter can be tested in that. Very simple. You just got to think about, the cycle's this. How do I define the reward? No problem, right? The problems will... Everything kind of sorts out that way. So this part looks here, and it should be clear that you're going to talk about this. So your reward is 1 here, and this, while you're getting this. And then the cycle is this. Okay. So I guess we're left with this part, which is either calculus or basic probability. We're left with how do we actually, in our case, we want the expected time to go from Atlanta to Boston over the expected time to go from Atlanta to Boston plus the expected time to go from, right? And we want to calculate these two expected values, okay? And let's just think about that. So expected time, if we write down the time to go from Atlanta to Boston, that equals, now we're getting distance between Atlanta and Boston divided by the rate. Now we're using dirt, right? Time, the time is the distance divided by rate. And so the expectation of time is distance, let's just call this distance. Distance divided, so I've got to say this the right way. It's the expectation of distance over rate times rate here, just straight away. So you don't want to jump too quick, so you then want to look at this. Right. This is a constant. The distance is fixed, whatever it is. So you factor this out, but you don't just move the e down here. So this is actually basic probability that you want to remember this. In general, that this is not going to happen. if you want the expectation of 1 over x, some random variable, it's not going to be 1 over the expected value of x. This is some function of x. So you think, well, what is this? Some function. This 1 over x is just some function of the random variable. And this is the integral of f of x, probability x equals x, dx, right? Or the density, if I write this. I've got too many. If I put a g here, and then g here, and then I have fx of x dx. So I have the expectation of g of x is g of little x times the density that x is equal to x, and I integrate. So that's what we need to do here. Okay, so when we want to go from there, we're looking at, so the thing is, what is now we're looking at this rate of going from Atlanta to Boston, and it's, what is it, uniform between 40 and 60, right? Uniform between 40 and 60. So you're going to, the key thing is this, what is this thing? This looks like between 40 and 60. Well, that's 20, so it's 1/20th dx. It's uniform. So there's this part. But here's a 1 over x here. This 1 over x is g of x. This function, this thing, is inviting you to, just like the half, it's inviting you to just slap the expectation down here, which isn't the expectation of, this is really expectation of some function of the random variable x. And that's just in general this. If I wrote this down, you'd surely write this. Almost everybody would do this. But this is so inviting that you'd kind of invites you to do this. Right? It just invites you to jump to this, where in fact it's this. So you're led to this, which is where the calculus, then you come to the calculus. Right? You're led to, the function is 1 over x, and then this is the distribution. The density is uniform by assumption on 40 to 60. So this is the density. So then you factor this out, and you're left with our, right? You're left with this integral of the reciprocal. Right? And then you get 1 over 20 log 60 minus log 40. Right? And that's the same thing, because log of 60 minus log of 40 is equal to the log of 60 over 40. Right? This is that, and so that's equal to the log of 3/2. So you're going to get this answer to be log of 3/2 over 20. Yeah. So when you do that, that's going to go here. So you're going to have, this is going to be distance times log 3/2 over 20. And then down here, you're going to get distance times log 3/2 over 20. And then you're going to get plus distance times the other term. The distances are all going to cancel out. Because you have them both, doesn't matter what the distance is. It will cancel out. So you're going to get this. So we have to calculate the other thing. We have the same kind of formula for the other one, right? So let's just, the other one actually, it asks you to do it in a discrete form. This problem really is totally illustrative of what goes on, I guess, in this course, is the main idea. This part is pretty easy, and the rest of the stuff is pretty hard, right? I mean, this is actually sort of typical and frustrating, because the main part, that this theorem was really easy, and yet implementing it all requires that you remember, essentially remember the first probability course in your calculus course and stay the course. This is illustrative of where the good answer, a half, isn't true, and you got to do something, and you're doing, it's not really hard, but you got to grind it out, and you got to think, gee, this is surely wrong. You got to have confidence then, right, that you're chunking along and you're doing these calculations, and it's okay. It's not really wrong. Okay, well, let's take the other one. The other told you're going, with probability half, you're going 40, and with probability 1/2, you're going 60. So when you look at this, B to A, this is D over D times the expectation of 1 over rate B to A. So you get 1/2 times 1 over 40 plus 1/2 times 1 over 60. Right? This is the expectation of 1 over the rate. It's 1/2 this, but it's 1/2 g of it. 1/2 1 over 40, 1/2 1 over 60. Right? Same reasoning. But now it's a probability, mass function instead of a density. So it's exactly the same reasoning. You've got to be able to compute E 1 over x is either 1 over, say, xk, probability x equals k, say, if we make it integers. Right? This is discrete integer valued. So if x is integer valued, we would put g of k, probability x equals k. G of k, probability x equals k, but it's 1 over k. So that's this, and there's just two values to consider, 1/2 on each, and here's the 1 over k on 40 and 60. So this thing looks just, it's just this, and this is just the discrete analog of what we wrote before for calculus. For the integral is just this continuous version with a density function, discrete version with probability. And it's just recognizing that that the expectation of a function of x such as this is just the usual thing, but this is not 1 over the expected value of x. So what does that thing become? This thing. So I guess it's 1/80th plus 1 over 120, right? So that's 3 over 240 plus 2 over 240 equals 5 over 240 is 1 over 48, right? So then down here we have d times 148. And you have this mess. They're frowning. Let's see, 180, 120, 3, 2 over 240, 5 over 2. Yeah, okay. You're looking, the chances are very high that I'll get it wrong. You're right. It's that if nothing else, you could you could try to just follow along and see when I screw up, which may be not unlikely, but it looks okay. So then the d's cancel, and you have this crazy answer with this ratio of logs and whatever. Not a half, right? This mess. But anyway, that's what it is. Okay, I guess I'm thinking that you see this problem in the various aspects, that you see that the fundamental renewal reward stuff is compelling and straightforward. You see that the probability part is, that's this, that this is not this, and what it should be is something you should know. And then this dirt, and you see, well, all that comes from the sort of basic understanding of the physics of the problem of the dirt. Distance equals rate times time. Okay. So let's see. To firm our understanding, I have in mind doing another problem. Again, I guess there's two parts, and I guess I'm thinking the renewal process part is again easy. This is that thing we just did was problem 38. So the important point was, what we did was number 38 in the exercises in the book. What we're going to do now is number 40. in this problem, 3 people are shooting at a target. They're marksmen, they're shooting whatever, they're shooting bows and arrows, whatever, they're shooting at a target. And the rule of the game is the 3 players, player 1 shoots until he hits the target. Shoots once, if he misses, he shoots again, and he keeps shooting until he hits the target. And then player 2 starts shooting until he hits the target. And then when he hits the target, player 3 starts shooting, and he shoots until he hits the target. So, and you either think of time measured as in numbers of tries, right? Numbers of tries, so it could be discrete time. Or you say, well, the expected time it takes for each of these guys to take a shot is 1. It's going to make it equivalent to not paying attention to the time differences, which you could add to this. They could take different times to shoot, which would be not change the problem greatly. But we could maybe think about that. If we still have time before the L word, we can think about that. But now we're thinking of the time as being 1. So there's 3 marksmen. We could give them names, but anyway, they have probabilities. Probability of hitting is P1 is equal to 1/2, P2 is equal to 1/3, and P4 equals 1/6. And then we say the proportion of time number 3 is shooting is, and before you write it down, you write down this, right? You just write it down, and the time it takes to write it, you do the calculation and see that it's 6/11. Right? That's not unreasonable that you would, 6/11ths here. Well, and what is that? That's, where does that come from? That's where if you see 6/11ths, let's see, how does 6/11ths fit this? You look at all the reciprocals, 6, 3, and 2, 6 over 6 plus 3 plus 2. At least that's sort of where the numbers must come from, right? That's, if it's, that's sort of, so now let's think about the probability problem. That's the answer. And I guess when this stuff is second nature, you would see that right away. You know, like if somebody was discussing it would be clear to you, such a problem, what the answer would be. So it helps you think about these things. But here's time. And now it's a little different than before. We have, we're going along, and so 1 is starting. So maybe we say 3 marksmen, A, B, and C. So A starts, and then finishes, and B starts, and then C starts, and then A starts, B starts, C starts, and so forth. So it looks just like the last thing, except we have the cycles are this. There's 3, A shoots, B shoots, C shoots, and A, you start over here. And by assumption, all these are independent, so the situation here looks the same as here. We have a renewal here, and we have another renewal here. And the cycle is one of these, is 3 of these things. An A time, A's shooting time, B's shooting, A's shooting, and here, A shooting, B shooting, so forth, in these intervals, and then C. So A is shooting, B is shooting, C is shooting, A starts again. So these are renewal epochs when A starts shooting. And so this whole thing from A, when A starts shooting until when A starts shooting again is a cycle. Right? And here, every shot takes 1 unit of time. So the only reason these are random is the number of shots they take. So we want to say the proportion of time that C is shooting proportion of time C is shooting. If I have these, I would have something like this. In other words, this is the expected number of shots by C each time. This is the expected number of shots by A, the expected number of shots by B, and the expected number of shots by C. In each of these, they're separate turns. Because time is always 1. Each time of each shot is 1. So the expected length of this in time is the expected number of shots A takes. And A shoots until he hits. A shoots until he hits. So this is the expected number of times A shoots. This is the expected number of times B shoots. Expected number of times C shoots. The cycle is the sum of those expectations. The thing we're interested in is C. This is the proportion of time C is shooting. This is the renewal reward process again. The reward is being given at rate 1 when C is shooting. You could be doing it in discrete or continuous time, right? So we have this. This again is the, this part is the part we're studying right now. Is not hard. Then you have the question of filling all this in of, again, this probably the hardest part is what are these 3 expected values that we need to plug in here. Right? That's actually the part, and you've all had that, and I've been doing this forever, and I tend to get this wrong all the time, this calculation. I might be wrong now, possible. Let's see, so let's do some of these calculations. So, if you're talking about, I guess the thing you'd remember is you're having a sequence of trials where they have a constant. They're independent trials, constant probability of success here, then the number of these things has a geometric distribution. So I guess the thing to recognize, the first step is to recognize that the distribution of each of these numbers is geometric. The confusing part is that there's you could define there's 2 kinds of geometric distributions. And sometimes one talks about the P being the probability of failure, sometimes of success, so you could get that backwards. So that whether the P refers to the probability of failure or of success, or what success means is confusion. And the geometric could be defined on 0, 1, 2, 3, or on 1, 2, 3, 4. And that's actually, so if you just started out and you said, well, let's just take this one. Let's consider the probability that the number of shots by C in any one term is K. Just compute that. So we would say, well, his probability, he's going to keep shooting as long as he fails. So this must be 1 minus P, well, he's number 3, 1 minus P3 to the K minus 1 times P3. He shoots K minus 1 times in succession with this probability, and then on the Kth time he succeeds, and that's the end of it. And then this is only true for K greater than or equal to 1. 0 is not an option here, right? He's going to shoot. He starts and he shoots. So 0 is not an option. So K is greater than or equal to 1. And this actually looks backwards from the way the thing in the book, you usually have this. Sort of looks like this, the geometric. This is the way I think of the standard geometric. Whereas this one is got the other way around. Okay. Yeah. Yes, express bother. You may have, your bubble may coincide with 30 other bubbles. Yeah. He shoots until he hits. Did I say miss? Oh, what does it say here? Okay, let's see, what does it say? Did I misread it? I'm just remembering. Where is this thing? Did I get it backwards? Okay. They shoot until they miss. Yes, totally backward. But these what are these probabilities? Okay. Each marksman. Okay, so there's an issue. So let's think about this. Okay, he shoots until he misses. So he shoots until he misses. Shoots until he misses. I didn't pay much attention. 3 marksmen take turns shooting. Marksman 1 shoots until he misses. Then minus. Okay. Shoots until he misses. Okay, thank you. Right? Shoots until he misses. That might be the answer is going to change if I didn't do that. So the point is, whether I put this as this or this is just a question of which I call it, right? So you're right. So if he shoots until he misses, then he hits this probability in this. So actually, I think I actually looked at the answer. I did look at the answer. So I guess Ross got it wrong too. So he had the thing switched around. So I just thought about it. I looked at those answers. The answer sort of goes like this. So if I'm having this, I'm having the shoots until he misses. Okay. If you're, yeah, not right. You may be bothered if I had this backwards. Yeah, okay. Shoots until he misses. Well, I'm okay. The problem was if you shoot until you hit with those probabilities, you shoot until you miss with this, it's the same problem. So actually what I wrote down is okay for my problem. It isn't what's in the book, right? The book has this, so I should change it. But actually his answer's wrong because his answer confuses those two. So if I do this, this is still, if I change it, probability shoot until he misses, and these are the missing probabilities, then these are the probabilities of hitting k minus 1 times and then missing, which is what the book is saying. And now I've changed this in such a way that it's going to be the right thing, except these are not right in the book. So my answer here goes with this and not with what Ross's answer is in the book. But you don't need to worry about that. Okay, so we have this. So then the thing you see, so let's just think of it in, if you see in the book, let's use this notation. Probability y equals n for n greater than or equal to 1 or n greater than or equal to 0, what is the mean? So you can just look this up in where the mean value is, and if it's this one, you see it's 1 over q, and if it's this one, it's 1 minus q over q. This would be this formula here. It's geometric, and well, if n's greater than 1, it should be this way, and if it's n greater than 0, that way. So the form for n greater than 1 has this, and the form with n greater than 0 has that. So the reason this is here is if you sum this from k greater than 1, this will start at 0, and this thing will sum to 1 over 1 minus this, which is this. So this will sum to 1. And similarly, these will sum to 1, because if you start here and here, right? And then the mean is just calculating the mean of this thing. So the mean of this with this thing will be 1 over P3. If we have k greater than 1, we're in this case, and now am I saying this right? Yeah, 1 over, did I do this again wrong? Let's see. So this case is, I'm doing this wrong, right? I want 1 minus q and q over 1 minus q. As I've worded it like this, I want this and this. And if, yeah, okay. And I get this. So I guess this is like I said, I'm getting this backwards all right. I guess I was all right in my writing the thing down with the hitting here and this, and so missing, if you change it all, the answer is going to come up to be this. I think this is right as I worded it, and that would be the answer in the book would be different because the meaning's different. So you'd shift these, it'd be 1 minus reciprocals. Okay, I guess the point to be made is this geometric distribution is easy to write down when you think about it. Oh, well, this is the probability of doing whatever k minus 1 times and then doing the next thing on the kth time. So you write this down, that's geometric, and you could have a geometric greater than or equal to 1 or greater than or equal to 0, and the mean the mean of this is 1 plus the mean of this, because everything's shifted over. Okay, Robbie, you're bothered. Okay.
Where you have a Q matrix, like instead of having the probabilities, can you think of those as rates and then solve?
Oh, and we might have had, suppose we had their times, if we had their times, suppose their times to shoot were exponential with a constant rate 1, right? Then we would have, we could make probabilities out of the Q matrix, right? Because they would be moving along. You'd be marching around, right? If we made the times to shoot, the length of time for each shot, to be exponential, then the whole thing would move along according, and there would be some rate to move to the, you'd be in state A, and you'd have some rate to go to B shooting next, and then there'd some rate to C shooting next, and then some rate to A shooting next. And you'd go around, and the rates would be different, and you'd solve the thing, right? So it would indeed do that. You could indeed do that. And in fact, this is an example, more generally, this is an example of a semi-Markov process. So we've talked about semi-Markov processes. So maybe that's a good reference point here. If we thought about this, if we made the process that x of t was equal to 3, 2, or 1, if shooter, 3, 2, or 1, x of t is equal to j, if shooter j is shooting. So we would then we would draw the picture that you're actually in, say, 1, 2, and 3. And so you're here some length of time, and then you jump here, and then you're here some length of time, jump here, and back down here. Right? So you're always going, and indeed, you're in 1, and then at this point you're back in 1, and at this point you're back at 1. So this is just another picture of the same thing. This is where the cycle starts. Now, the question is, if you made these times in shots to be exponential, this could be modeled as a continuous time Markov chain. This would be a continuous time Markov chain where you'd be, in here there'd be a rate that you'd go here. And then here there'd be a rate to go here, and here there'd be a rate. But without that structure, regardless of what you put here, the semi-Markov process, you see the discrete time chain that's here is very simple. You always go from 1 next to 2, and from 2 next to 3, and from 3 next to 1. So if you did the semi-Markov process view, if we used our notation would have been alpha j is equal to the probability is equal to the limit as t goes to infinity that the probability x of t is equal to j. So this is the limiting steady state probability here, which we would solve in the exponential case. We would have solved alpha q equals 0, or it would be a birth-death process as well. No, not a birth-death, because you go up 1, up 1, up 1, but down 2. So it's a continuous time Markov chain. But the discrete time chain, the semi-Markov process view is very natural here. You take P1, we're interested in Pj over P1 plus P2 plus P3, but then you want to multiply by the mean time that you spend in each of these states, which we were often using 1 over nu. In the continuous time Markov chain would be this holding time, which would be this. Okay, the semi-Markov process view would be that you solve the discrete time chain, but here it's obvious that the discrete time chain steady state distribution is 1/3, because you're going from 1 to 2 to 2 to 3, 3 to 1, and so forth. You're going around. So the long run fraction of time that you're in each of these states is 1/3. So then the thing that you're doing the probabilities, so these 1/3 will all cancel, and you're left with just the mean time in each of these states over the sum of the means, which is just the formula we had up there, this, right? It's this formula. And it doesn't depend on the underlying probability distribution, except if you made the times you spend in these states per shot different, you would have to say your MJ would become, right, you would say EMJ is equal to ENJ times the expected time. So this means this mean time, this is the mean time J is shooting. So this is the probability, the long-run fraction of time J is shooting, and this is the mean time. This mean time would be the expected number of shots by J per turn and the expected time per shot, which we were saying this is always 1. But if these were different for the different ones, you'd plug this in the same way. And this is just looking at this semi-Markov process view, which is a section in this chapter, is just exploiting this renewal theory structure again. So this story is the discrete time chain is telling you where you are at transition points, and then these are the mean times you spend there during each transition. That is what? It's somewhere we're going to discuss it, section 7.6 or see, let's see. 7.6. Well, I guess a takeaway message is really that there is this simple story, expected reward per cycle divided by expected length of cycle. And in this case, this reward's just when you're in this state C. So this expected length of the cycle and expected reward per cycle notion is pretty, that's the easiest part. And it's the same for all these problems. And that would be what this is too. Okay, then I guess, and the part that as demonstrated, I guess, when I'm doing the geometric distribution is you want to be careful to do the geometric distribution right, the right one. It could start at 0, it could start at 1, all the stuff about the geometric distribution, and compute its mean properly. And I mean, you can always check if the mean, I mean, I guess I do that when I'm sitting there. Did I use the right formula? If I make P bigger, does the answer change in the right way, right? I mean, you think, well, that's actually when you get muddled, you might write the wrong thing down. You'd say, oh, if my probability of hitting goes up, I'm going to spend more, depending on what you figure out, change the parameter some way. Is the answer consistent with obviously the question should be? So you can check that you didn't do something stupid. Or if you know you're going to do something stupid, you can correct it in that way. Okay. Okay, let's see. So I had in mind, but I didn't seem to, okay. But we covered what I mostly wanted to talk about. Let's see. So there is some point in concepts. Let's just talk a little bit about definitions here. There are going to be some concepts here, and I'll just sort of emphasize these things a little bit. A regenerative process, semi-Markov process, alternating renewal process, and I guess, let's see, 1, 2, 3. So I guess an alternating renewal process is a special case of a semi-Markov process, which is a special case of a regenerative process. I guess we'd have a well, renewal process doesn't quite fit, would be in here. So let's think about what these things are. So we might have, in this case, In the alternating renewal process, well, we're going to have a stochastic process. So we have a stochastic process. And it might be a regenerative process, might be a semi-Markov process, might be an alternating renewal process. In the alternating renewal process, we might make x of t equals 1 or 0. So then you would have this picture as we drew it would be here's 0 and 1, that you spend some length of time and you do something like this. And there are these x1, y1, x2, y2, x3, y3. Let's see, if I'm using x's, let me make y1, z1, y2, z2, y3, z3, y4, z4. And we're assuming here that the y's are independent and identically distributed, and the z's are independently and identically distributed, and all of these are independent. So you have these uptime, downtime, say, whatever you have some random time, another random time, and at these points, when you have two of these, so this is an alternating renewal process in that you have two random variables, but together the sum makes a renewal process, because these will be starting over every time we enter 1. We enter 1 here, so maybe we're entering 1, we enter 1, we enter 1, we start over at all these times. So there is embedded in this process is a renewal process. An embedded process is if we look at these times. So there's, but the alternating, so if it's x of t we're thinking about, it would be this stochastic process, but where they would be these embedded x's, y's, and z's, which are the times we spend in 1, times we spend in 0, time, so forth. Now, if we thought of the renewal process, we might use for notation of the renewal process a standard, if we use n of t for the renewal process. And if we use, let's say, t1, t2 as times between renewals, and then Sn as the sum of these would be the renewal times. Then in this version here, the Tj is Yj plus Zj, right? In this picture, the renewal times are these cycle times. And at each t is t1 is y1 plus z1, t2 is y2 plus z2, and we have this renewal process counting up to time t how many of these there are. So let's see, if I redrew this, I could draw them both on the same picture. I'm still having y1, z1, y2, z2, y3, z3, so forth. If I did a renewal process, I would be counting when the cycles occur. So I come here and I have 1. And I'm going to when the y starts, and I have another one. And then when the y starts, and so forth. So this would be n of t would be this here where this is t1 and this is t2. So associated with this x of t is an embedded renewal process. This is embedded we have this stochastic process, x of t, which is going from 1, 0, 1, 0, 1, 0. But at the times, at these regular times, there are these starting over points, which make a renewal process. So inside x of t, in its construction, there's this embedded renewal process. That notion applies to all these things. So the idea here in this most general thing, the regenerative process, is you have some very general process where there are these renewal times. So let's see if I did it as do a picture of that. So a standard example is a fairly complicated queuing model, but with lots of independence. So I'll draw a picture of a queuing thing that's complicated. There's a queue. Let's say it's a single server queue, but with non-exponential service times and inter-arrival times. In the queuing language, this is GI1, not MM1, where it would be everything would be exponential. So what's happening? At this point here, at these special points, things start over. At this point, you have an arrival time to an empty system. So there's no history of the arrivals, and there's no service. At these other times, at this instant, this arrival starts service and has some random service time, which is not exponential, so it doesn't have the lack of memory. So at this point, the arrival starts over, but you're still in the middle of that guy's service. So you don't have the Markov property. And so on, you have arrivals and departures, and sure, at each change, if it's going down, you have a service completion, so you're going to start a new service. But at that time, you're still in the middle of the last arrival. Things are still messed up in terms of the Markov property. You're fine here. It's empty. You just had an arrival, so you're starting a new arrival time and you're starting a new service time. But everywhere else, when you have an arrival, you're in the middle of a service, and when you have a service, you're in the middle of the arrival. So you don't have lack of memory. But when you get down to here again, now it's empty. You're empty, but you're in the middle of an arrival time. But at this point, it starts over, because it's a new arrival and there's just nobody there, so that guy is starting service. So this point and this point are points where everything here looks just like it did here. The history has no matter. And actually, this is very powerful. Just the fact, even though this is complicated, it starts over at all these times. And you might call this process a queue-length process. Well, we can use the same notation, x of t. It's recording how many customers are in the system, so it's going up when there's an arrival, down when there's a service. And it's nothing nice. It's not Markov. But every time the system has an arrival, when it's empty, it starts over. So there's an embedded renewal process. And that's what we mean by this. A regenerative process is a very general process that has an embedded renewal process. And that enables you to do lots of stuff with it, which is discussed in the book. In other words, you can exploit that stuff. I mean, you then define this as a cycle and start doing stuff, at least conceptually, you've got a hold on this problem because it starts over. It's essentially trying to do the Markov property, all the stuff we do, Markov chains, discrete time, continuous time. You're always exploiting the Markov property. Here, the Markov property only holds at these special times, but you use that. And this has got a similar thing going on in the semi-Markov process. That rant and rave got us from the end of the second problem to lunch. Okay, now we can, all of us, in good conscience, can advance on lunch. Okay? Let's do so.